Gaitsgory from the Max Planck Institute about the proof of the geometric Langlands standard.
It's a great honor. So over lunch, I was complaining about it being symposium. So there are three main characteristics of the symposium. First of all, people must be reclining, not sitting. Second, very importantly, people must be consuming wine. Like, what is this? And thirdly, I think the discussion, at least the talks, must be interrelated. I'm not sure I'll be able to connect my talk to Camilla's talk, but at least with Juvé's talk, it's basically introduced all the players that we use. So, continuation of what you were talking about. All right. Without further ado, Langlands is an equivalence of two categories. There's a left-hand side, right-hand side. So let me tell you what the left-hand side is, what the right-hand side is. So our input is smooth, complete algebraic curve, like in Juvé's talk. Over some field K. Now already there is not a bifurcation, but a trifurcation. So there are what you might call different sheaf theoretic contexts, and there are three different flavors of geometric Langlands. So one context is what I call the Rham, and in this case, so A is arbitrary field of characteristic 0, and what you will do is that when you have a geometry over this field, some scheme, call it Y, consider the category of P modules on Y, whatever it is. So there will be three flavors. You can choose one that is your favorite point, or one that you know. So you don't worry if you don't know what D modules are. And let me just say that whenever I say a category, I mean always mean a derived category. In fact, I don't even mean that. I mean some infinity categorical enhancement of derived category. So the most important thing is that in this context, this is a category. It's linear. You can take direct sums, but it's also linear over the field K. And like I always keep the notation E for the field of coefficients. So in this case, this field of coefficients of my category is the same as the ground field K. So another context is what's called Betti. And in this case, your ground field is specifically C, and what you do to an arbitrary scheme Y over C, you can attach the line topological space, and on it you can consider the category of sheaves of vector spaces over an arbitrary field E. So let me write sheaves Betti Y with E coefficients. So here is E is arbitrary. Or you can take l-adic sheaves, and in this case, K is arbitrary. And to Y, you attach category of l-adic constructible sheaves. And in this case, the field of coefficients is Q bar. And sometimes I'll write just sheaves on Y, indicate any of these three, if I don't want to specify. All right. Okay, so yeah. Assuming that. All right. So going back to defining the left-hand side, itself G, a reductive group over K. And as in Juvé's talk, we consider a geometric object. It's this bun G. It's the moduli space of principal G bundles on the curve X. This is our geometry that we'll study. And so, geometry will associate a category exactly in this way. But let me first consider the Rham context.
Until X.
Yeah, but I don't usually write X. I can now, but I'll forget later. So, and this is the geometric side of geometric Langlands. So, geometric side of geometric Langlands. So again, this is a category over linear over the same field K that we were. So now I'll describe right-hand side, also called the spectral side. So the object is also associated with the geometric object, and that geometric object is called the stack of local systems with respect to the Langlands dual. So assume that you guys have heard that every reductive group there corresponds to Langlands dual, which is also a reductive group. So what will happen is this reductive group depends on the context. So in the Rham context, it will be again over K. And this is an algebra geometric object over K. It's not algebraic variety like was this one. It's an algebraic stack. X here. So I'll define it in a moment, but the category that you will consider is the following one. So you take the category quasi-coherent sheaves on it, modulo a small lie, which I'll explain in a second. So let's let me say what this object is. So it's the stack of the Rham local systems, as we perceive them. So these are bundles with respect to this group equipped with a connection, and the connection is automatically flat because you are over a curve in dimension 1. So the flatness condition takes place automatically. Again, so modular space of bundles with a connection. And this is an algebraic stack over K. There are quasi-coherent sheaves on it, and it's again a category linear over the same K. So the slight correction here. Okay, before I say this, let me just, there is a kind of funny dichotomy here. So here we consider just bundles, but on the space of bundles we consider D-modules, and here we consider bundles with a connection, and on the space of those we consider just quasi-coherent sheaves. So like the connection gets traded off. So the slight correction is that it's not quite quasi-co, it's a modification that's called int co nilp, and there is no possibility to discuss it in 1 hour talk. Just think of it as you just tweak this category a little bit, and this tweaking has to do with the fact that this modular space is singular. And what happens is that, so again, we are working with the derived category, and you modify this derived category at the cohomological negative infinity. So you do something at the end to make the spectral sequences converge. So that's what it's about. So, and the first version of geometric Langlands conjecture, call it functor L, the Rham incarnation, is that we have an equivalence again. The equivalence is really with this. Oh yeah, so first of all, I should say that it's a joint work involving people whose names I have trouble listing alphabetically. So Arinkin, Beraldo. So now it's English. A-B-C Campbell, Justin. I told him to, he's still here. I told him to not to attend the talk. Chen. This is Lin Chen. So Faergeman. Then Kevin, who's in the last row. Sam Raskin, who was here last week, last week, 2 weeks, and he gave quasi the same talk. Will you tell me if it was exactly the same? And Rozenblyum. All right. So that's the first theorem. So and now what I'll do, I'll describe kind of its version in these other contexts, and I'll tell you how they are interrelated. Any questions so far?
You think these are the only three contexts in which things will work, or do you think it might also work, say, with crystalline coefficients in characteristic P, or this new theory of?
It might very well be. Just, I haven't gone there.
Okay.
But I mean, it's very worth studying. I didn't have the brains. All right. Now let's go to the spectral side. And so the spectral side, it's easier to start with these, Betti context. But it's easier to start with the spectral side with the Betti context. So what we do, we write here local systems in the Betti sense. And I'll tell you in a moment what they are. So again, now your algebraic geometry is over C, and you perceive the X as a topological space, and local systems are really it's the modular space of representations of its fundamental group into G check. So it's this modular space of homomorphisms from pi1 of X into G check modular conjugation. Modular conjugation is what makes it an algebraic stack. It's kind of a very naive object. And you play the same game. You take quasi-co and you modify it in the same game. All right. And so now let me try to do the geometric side. Well, I'll write Bang G. And I want to write sheaves Betti. Yeah. So here I should remark that so Betti context, we chose this field of coefficients, and this G check is an algebraic group over the field of coefficients, and this gadget is an algebra geometric object over the field of coefficients, over this E. And so this is category linear over E, as is the left-hand side. So we're comparing not apples and apples and not apples and oranges. So we want to write this, but it will be incorrect. And this correction is something that I'll explain next. So let's consider the simplest possible case when G is GM, the multiplicative group, like in G-raised talk. So we start with this always with this example, in which case G check is also GM. And let's look at what's happening here. So as I said, you're considering homomorphisms from the fundamental group into GM. So what's the space of these homomorphisms? Forget conjugation doesn't. Group is a B in any case. So this is just 2G elements of GM. G is the genus of a curve. So log sys GM is like GM to the power 2G. So let's see, what is 2 quasi-co of sys GM? So it's quasi-coherent sheaves on GM to the power 2G. To specify, so this variety is affine. Like, what's a quasi-coherent sheaf? It's a vector space on which 2G invertible operators act. So it's written as representations of the group Z to the 2G modules. And you realize that here we have this Bunge's Picard. And you realize that this Z to the 2G canonically appears as pi1 of this Picard. So you have representations of pi1, and what are these? These are what we call local systems, or Betti sheaves that are locally constant. So what we see in the case of GM is that quasi-co log sys GM curve is isomorphic not to all Betti sheaves, but you put here an adjective. So there are many equivalent adjectives. You can call Lis or locally constant. That don't change. Look, they are locally constant. So this is the true statement, and that's what we want to emulate in an arbitrary case. So, and what do you do? So the answer is the following. It's you need to put here nil. just to say that this nilp has nothing to do with this nilp. It's a very different nilp, and I'll explain what kind of nilp it is. And so the fact that we have to put this nilp, it was a discovery of Bensby, Nadler, and G. Wade. This is the right replacement, and somehow, like, basically the fact that we figured out what to put here got the whole theory going. So I haven't yet explained what it is. I'll do it in a moment. But so this will be the Betti incarnation of geometric Langlands. So now, who is this nilp? So here's the context. So if you have Y, algebraic variety C, and if you have a Betti sheaf, can attach to it what's called singular support. It's a theory developed by Kashiwara and Shapiro, and this is a subset in the cotangent bundle of Y. And vice versa, you fix a subset in the cotangent bundle, well, you can attach to it the full subcategory inside Betti sheaves, consisting of those guys. So these are Fs such that their singular support is contained in M. So in our case, Y is Bung. And so then we have to look at what is T star Bung. I'll explain what it is in a second. And inside there is a subset, it's called the nilpotent cone. So that's the meaning of this nilp. So if we take this construction, or M being nilp, let me tell you what the nilpotent cone is. So I'll explain it in the case when G is a GLN. And the general case I'll leave to your imagination. So Bung classifies for GLN. So Bung, and exactly as Juve's talked, Bung classifies rank n bundles. Now, so you can compute the cotangent spaces using deformation theory, and what you'll see is that a point in T star Bung is a pair. It's a rank n bundle and what's called a Higgs field of A. And it's a map from your bundle to the bundle twisted by the canonical sheaf. And so inside the nilpotent cone is the locus where this A is nilpotent. So because this is line bundle, trivially you can locally trivialize it. You can think of A as an endomorphism, and you can impose the condition this endomorphism be nilpotent. And that's what this nilp stands for. So A is nilpotent. Right. And so that finishes the definition of.
Could you unscramble this for us a little bit more? If you, SSF means sort of the directions in which F is allowed to change.
Right.
What does it mean here? Can you unscramble that for us a little bit so we understand what it means? It means that.
Yes, a little bit. So, for example, inside Bung, there is this mysterious open subset called very stable bundles. What they are is that the bundles for which there are no nilpotent Higgs fields. And on this locus, the guy is locally constant. And then you can explicitly describe, so like in characteristic zero, like we are here, the nilpotent cone is Lagrangian. It's actually it's the union of conormals to some locally close varieties, which you can describe explicitly. And in characteristic zero, it will mean that sheaf is locally constant with respect to this stratification. So, all right. Okay, so the next step is so we did the de Rham theory, we did the Betti theory, now we want to find a common denominator between the two. So what I mean by this is the following. So let's take A to be C specifically, and we take E in the Betti theory to be also C. So here we have D modules on some given Y, and inside there is a very special subcategory of D modules which are polynomic with the regular singularities. It's some condition that D modules is polynomic means that it has the smallest possible size. And so in the Betti theory, we consider also a full subcategory, which is, well, it's called constructible. So let me explain what this means with an example. So so these are really all Betti sheets, just all of them. So constructible means the following. First of all, there must exist a stratification such that when you restrict to the strata, your sheaf is locally constant. But that's not all. So let's even consider the locally constant case, like we considered for the Picard, kind of important. So when I talk about just locally constant sheaves, I really mean all representations of the fundamental group. And this representation may be infinite dimensional, and I'm not requiring that the fundamental group acts locally finitely. Huge thing. Constructible means that acts in a locally finite way. So your local systems are unions of finite dimensional local systems. So it's like two conditions. It's like local constancy along the stratification, and also this local finiteness. Okay, the point is that there's a famous theorem of Riemann-Hilbert correspondence that says that these two categories are equivalent. They sit in two very, very inequivalent categories. And so this is what I call the common denominator between the Rham and Betti theories. So, and a natural question to ask, can we find a common denominator to our left-hand sides of Langlands? So will it correspond to anything on the spectral side? So that's what I'm going to address next. I have to sacrifice something. I guess I'll sacrifice that one. So, well, I wrote this possible sheaf theoretic context, but now so I'll replace them by the following. In the Rham setting, I'll write D mod polynomic regular singularity Y. In the Betti context, I'll write sheaves Betti constructible. And the l-adic context, I'll write just the same thing. Nothing changes. So basically, the l-adic context is already constructible. And so I'll want, and before I called the big categories just sheaves, and I'll refer to any of these as sheaves restricted. All right, so and what I want to take on the left-hand side, I'll take sheaves restricted on Bun-G of X. And again, so what I mean is that in any of the contexts, I take this category, any of these. And what the beauty will be is that Langlands will look uniform across all three contexts. It will be the same thing. There won't be change on the. So the left-hand side will look the same, and the right-hand side will look the same in all three contexts. So we take sheaves restricted, but because we already know that in the Betti context, we had to put this condition of nilpotent singular support, we have to put it here. So the thing is that the notion of singular support makes sense for all D modules, and that has been known for a long time. And turns out that it also makes sense for l-adic sheaves. That's a relatively recent development. So it's due to Sasha Belenson and Takeshi's side. So main breakthrough happened around 2016. So we have this category. And so that will be our left-hand side. And now what will be the right-hand side? So I'll write log sys G check of X restricted. It will be a new algebra geometric object, which I'll fine. So it's a new gadget. And we'll have a restricted version of Langlands, which will say that category on the left-hand side is equivalent to the category on the right-hand side with the same kind of correction. So nil to replacing quasi-co. So this is what I'll call a restricted Langlands. Okay, so what I'll do now, I'll explain what this geometric entity is. Right. So to explain it, we'll have to take a slightly less naive point of view on the stack of local systems. So in the Rham setting, I just wave my hands. I say, oh, just take bundles with a connection. And in Betti setting, I say, oh, just take homomorphisms of the fundamental group into your check. So now we have to get a little more, not rigorous, but systematic. So let me give you a kind of a Tannakian definition of the Rham version of the stack of local systems. So I'll say what the Grothendieck functor point is. So for a test scheme R, from spec R to log sys de Rham is the following. It's specify map like this is the same as to specify a symmetric monoidal functor from the category of representations group to check to the following category. You consider the category D modules on the curve, and inside you consider R modules. In other words, you consider D modules with an action of R. R is the ring of functions. And so this is kind of this Grothendieck language definition of stack of de Rham local systems. Now let's give a similar definition in the Betti context. So again,
Strictly symmetric model?
as opposed to Planck's? Strictly, yes. Yeah, tensor product goes to tensor product.
Yes. Well, tensor product squared is the identity.
Yes, it's yeah, it's strictly symmetric monoidal, which is in the strictest possible sense. So now let me do the same in the Betti context. So this is again symmetric monoidal functors, but the target is different. The source is the same. You take Rebji check, and here you take all Betti sheaves, and you take R modules inside them. So in other words, you consider Betti sheaves on the X with an action of R, or you can think of them as Betti sheaves, not of E vector spaces, but of R modules. It's the same thing. And by the way, because this category is what we call rigid, image of this functor always gets you local systems. Parenthetic remark. Okay, now, so having this definition, we can define what local system restricted are. So this is the same. It's symmetric monoidal functors from the same thing. But here is your target. So you consider R modules in sheaves restricted on the curve. I emphasize when I take sheaves restricted, I wrote versions, but I always, when I write a category, always allow infinite direct sums. It's like not literally constructible sheaves, but like unions of such. And so you should see that this is, like if you compare it, for example, with the Betti version, it's drastically different. Actually, it's this local finiteness issue that I alluded to. So here, like local systems, but so these are local systems in which I1 doesn't act necessarily locally finitely, and here it does. So it makes a huge difference. Now let me just also explain how this geometric object, how it relates to the previous existing ones. So consider local system restricted the Rham flavor, and it sits inside the initial the Rham, and it sits as follows. It equals, so it is the disjoint union of formal completions of closed loci with a given semi-simplification. So, and from a certain point of view, algebra geometrically, it's a huge beast. It's kind of uncountable disjoint union of formal schemes. And you would think, oh, why would I ever consider such a beast? But it turns out to be immensely useful. And the reason that it looks so awful, that is the reason why people haven't discovered it before. Because like, why would you ever consider such a thing? But it turns out that there are some benefits to considering. And it's the same thing.
It's close to what number theorists thought about.
Say again?
When you say people didn't discover it before, isn't it close to how number theorists used to?
So we had this discussion, like, yeah, so you remarked that number theorists had thought about it.
Kind of, I guess.
Yeah, but kind of nobody in the geometric language community did. Exactly because it looks so strange. Well, I mean, when I first came across it, I ran by Mark Kissen. He said, what? So this is, in the Betti context, it also looks the same. You take your favorite, it's a nice algebraic stack, and you consider its closed loci with given semi-simplification and take the formal completions. That's what it looks like. It's really different. So, okay, so now let me tell you kind of the status of things and how we see it.
You don't this on the right hand side, it's a category of what was the add the right hand side.
Say one more time.
The obvious this is subcategory of without the
Yes. So in the de Rham context, when we have both the big and the small, it's a full subcategory in the bigger category of things that are set theoretically supported on the disjoint union of this closed loci. So basically, in other words, if you take a scheme theoretic point, if it lands, say it, theoretic point of a sub-scheme which is not scheme theoretic, which is not set theoretically contained in, say it, which doesn't correspond to fixed semi-simplification, then the fiber would be zero. And this kind of thing. So it's the same for Betti, but for l-adic, we don't have the ambient thing. For l-adic, we only have that guy. So here's the logic of the proofs. So we first prove GLC for the big de Rham, like the first one that I wrote, and like that uses heavily the machinery. Here we use D modules, quad D modules. So we use constructions of D modules by generators and relations. So it's in some sense a very geometric, non-geometric proof. So from it, but we show that it's actually equivalent to GLC or restricted de Rham. And then we apply Riemann Hilbert, and we show that this is equivalent to GLC or restricted Betti. And then we show that actually restricted Betti is equivalent to GLC non-restricted Betti. Just Betti. In addition, from here, we deduce GLC for l-adic, but so far when the ground field has characteristic 0. And so I'll say what we can prove when the ground field has characteristic P, which is the most interesting case. I'll say it in a minute.
The GLC for restricted PR, is that the regular singularity condition built in there or not? I got lost there.
Great question. So what it turns out, we prove separately that if your sheet has nilpotent single support, this nilpotent is Lagrangian, so it's automatic holonomic. That's not the question. So one of the kind of main structural theorems will show that these guys all have automatically regular singularities. It just so happens. So kind of test case, like a Abelian case, in this case, the variety is proper. So, or anything which is locally constant has regular singularities. And it's some miracle that occurs on 1G that this also happens.
That's the problem for going to
No.
Well, replication is not the problem.
Well, it of course it's Weil ramification, but not that. So I'll say in a moment what we can prove. So the theorem in characteristic P that so you can consider sheaves nil l-adic G isomorphic to this int-co nilp of disjoint union of some of the connected components of both is restricted. So this is subunion so what we don't know is we hit all of them. So like basically what we don't know, like in plain terms, we don't know the hard direction of Langlands. Namely that for every local system, there actually corresponds an eigensheaf. So we don't know that, except for GLN. Except GLN, in which case we know it. Okay. So I now slightly deviate from my original plan. I kind of want to connect it more to what Jive was talking about at the end of his talk. After all, it's a symposium. So let me assume this conjecture in characteristic P, and I want to derive something from it. So I want to derive from this form of geometric Langlands a classical statement. Okay, so I'll write it again. So we're assuming that sheaves nil l-adic 1G is equivalent to int-co nil. Again, pretend that this is just quasi-co on this losses G check restricted. So and assume, so now we work in characteristic P. So assume maybe specifically at P bar, but assume that your curve and G are defined over F cube. This case, both left hand side and right hand side carry Frobenius. Level of categories Frobenius is self-equivalence. So both sides self-equivalence used by the Frobenius. And so what we're going to do next, we're going to take the categorical trace of the Frobenius on both sides and see what we get. So let me just say a few words. The categorical trace. So sorry.
How many? Yeah.
So you consider the stack of local systems. So on your geometric curve, just pull back your local system with respect to the Frobenius automorphism. That's the Frobenius endomorphism, and that's the Frobenius automorphism.
Right. Left.
Left hand side. So all I mean is the following: that you on G is your now geometric object defined over FQ, and just pull back with respect to Frobenius on it. So that's what I mean. Good. Right. So what do we mean by trace? So who knows how to take a trace operator of finite dimensional vector space? Well, what you do is this. You say that here's your finite dimensional vector space. It has a dual. It's very important. And the dual means that this is your ground field. So there is a unit map. And let's say your operator is T. You apply T times identity. You go to V tensor V star. And then you apply the evaluation map. So this is a linear map from K to K, i.e. scalar. And that scalar is the trace. Trace of T and V. So now this operation has nothing particular to do with finite dimensional vector spaces. It makes sense on an arbitrary symmetric monoidal category, where instead of V, you take arbitrary object. It's called dualizable. In other words, for which there is a unit and co-unit map that satisfy the usual axioms. So let's say O ambient symmetric monoidal category, and C is a dualizable object. O, and T is an endomorphism of C is an object of O. So, and the trace of T on C will be what?
What is C again?
C is an object on which we're taking the trace. The trace is, what kind of thing is it? No?
Unit object.
Unit object. Unit. Yes, it's an endomorphism inside O of the unit object. Okay, and now we'll play the following game. So our O is DG cat. It's the category of all DG categories. So forget DG, it's like linear categories over a given field. And our C, so C's are DG categories. Now there's this tricky condition of what it means to be dualizable. But so one thing, basic fact is that every category that's what's called compactly generated is dualizable. So forget it. It's like really technical condition satisfies it, like 95% of examples. So therefore, if C is a DG category, such as like sheaves and something, and if T is an endofunctor, you can take the trace of this T on the DG category, get what? Yes, you get a vector space or complex of vector spaces. The unit in DG cat is vect, and endomorphism of vect is vect. It's like endomorphism of K where it was K. So the trace of an endofunctor on the category is a vector space. And that's what we're going to do. So we have this equivalence of categories. Compatible endofunctors, we're going to take the traces. So from this form of Langlands conjecture, we obtain the trace of Frobenius on the left-hand side It's isomorphic to the trace of the Frobenius on the right hand side. And I'll now calculate both, and we'll see something interesting. And then I think then it will be the time to finish. Already, I know. Great. Okay, so take an arbitrary variety, stack or whatever, over FQ bar defined over FQ. In this case, consider all sheaves on this variety Y. The category has an action of the Frobenius. And you can consider the trace of the Frobenius on sheaves on Y. Again, I'm thinking of Y as living over FQ bar, but is defined over FQ. Now, if you think of, now there's a famous Grothendieck's passage from sheaves to functions, and what if you think of what it actually does, it defines a map from this vector space to the space of functions Y on the set of FQ points of Y, dual bar coefficients. So properly understood, Grothendieck's passage is this map. But this map is not at all an isomorphism. So like it's surjective, but this is really a vector space in cohomologically degree 0. This we don't know, like it may live, obviously lives in many cohomological degrees. It's surjective on H0, but it kills a lot of stuff, so it's really not an isomorphism. But let's play this game specifically for Bungie, Frobenius. So I take trace of Frobenius on sheaves, all l-adic sheaves on Bungie. And as I said, have this map. So I should say also with compact supports, because the Y may be non-quasi-compact.
It's why you have star there. It's
not this.
No. 2-8 bar.
Put random symbols in the word. So functions on Bungie. But we have another player. We can consider trace of the Frobenius not on all sheaves, but specifically on our weird subcategory of sheaves with nilpotent single support. So there is a functor, this including functor, it induces a functor between trace of Frobenius vector, trace of the Frobenius, and we can consider this composite. Now there is a very surprising theorem. This is the so it was it's Arinkin, Kazhdan, Raskin, Rozenblyum, and Warshawski, and it's only thanks to the coronavirus that it came into existence, because we all had time to just think. So it says that this composite map is an isomorphism. It's a really surprising theorem because it tells you that the space of automorphic functions, was alluded to in Jouvet's talk, is actually the categorical trace of Frobenius on something. So this theorem was the first direct passage between geometric Langlands and classical Langlands. So this category is geometric, and there is an algorithm how to produce from it the space of automorphic functions. So this is what this theorem says. So composite is an isomorphism. All right. So right here, so this is, as I just wrote, it's the space of compactly supported functions on Bungie of Q, the values of QL bar, aka the space of unramified automorphic functions. Now let's deal with it right hand side. So there, the situation is as follows. So if you take an arbitrary Y, algebraic geometry, and let's say phi is an automorphism or endomorphism, you can calculate the trace phi lower star on quasi-coherent sheaves on Y. And if Y is reasonable, that's what you're going to see is that this is always the space global sections of the structure sheaf on the fixed point locus. Basically, if you apply the definition of trace, in this particular example, by some base change, you will see that. This is for quasi-coherent sheaves. But, so now I didn't say what incoherent sheaves were, but I said that it is just really minor replacement, but this minor replacement really plays a big role when you start taking traces of the Frobenius. What happens at negative infinity somehow becomes highly relevant. And what you see is also sections on the fixed point locus, but no longer of the structure sheaf, but of the dualizing sheaf. So here it's not in co-nilp. It's not in co-nilp, but it turns out that this nilp plays no role. So, and I'll introduce a notation. I'll write log cis. Pardon me?
Look, there's a map from one to the other.
There is a map from one to another. It's a little bit non-trivial. So what happens is that this fixed point locus is always Calabi-Yau. There's a map from, yeah. So I did introduce now log cis arithmetic, and it's the derived fixed point locus of the Frobenius on this log cis restricted. And so points of this are exactly arithmetic local systems as you perceive them. This is really representations of the arithmetic fundamental group of X into G check. And so, and this definition gives it a scheme theoretic structure, and it turns out that this is, so this guy was horrible, like disjoint union of this formal stacks. This is actually an honest algebraic stack of finite type. So there are alternative definitions of this guy. One is due to Shin-Wen-Zhu, the other is to Schulze, but you can show that they all three arrive to the same notion. So it's like the actually no ambiguity as to what this guy is. So what we obtain is that this is global sections on this log cis G arithmetic of the dualizing sheaf. And so if you trace this sequence of isomorphisms, you obtain an isomorphism like this. And so what it tells you is that it gives you a full description of the space of automorphic functions in Galois terms. It says that it's basically what Langlands wanted. So here you can ask, the space of automorphic functions on G in terms of Galois representation is what? We say, okay, there is, first of all, there is algebra geometric object that parameterizes them, this type of arithmetic local systems. Naively, you would think you would just take global functions on it, but no, you have to take the dualizing sheaf, and it's drastically different because the space is badly singular, and you take global sections. So this is the answer to Langlands in an unramified setting.
What happens? GLM. So is a claim that so then should be bijection, right, between Caspidal.
Yeah. Yeah. Yes. For Caspidal, the Caspidal locus is smooth, and then it's just really kind of a bunch of singletons. And it's not just GLN, it's for. So what this says is that on the Caspidal part, it's really one-to-one. Caspidal unramified functions are one-to-one with irreducible local systems. Like all this mess with omega begins with at the reducible locus, it kind of takes care of Eisenstein series.
So you're saying that this multiplicity one holds for
Caspidal,
for
yes.
any G.
Yes. Surprising, but and multiplicity one is a theorem because I said that there's like so because only get some of the connected components. So the fact that multiplicity one is a theorem. We don't know multiplicity less than or equal than one is a theorem. So like
You feel the space is singular? How singular is it?
what we call quasi-smooth. So quasi-smooth is it's derived locally complete intersection. It means that cotangent spaces are in cohomological degrees 0 and -1, and quasi-smooth mean cohomological. And that implies that That plus Calabi-Yau would mean that omega equals O, but this guy has potential spaces degrees 0, -1, -2. And so the structure sheaf in this case goes off to negative infinity, and omega goes off to the positive infinity.
How far
To infinity. So they're kind of the infinite. So like omega equals O on the quasi-smooth locus, but when the singularity is really bad, they kind of go in the opposite directions.
The fact that omega is unbounded makes it kind of shocking that this global sections is classical, right? Like,
It is shocking, but it's true.
There's no a priori reason to.
No, that's the only reason we know it.
Question?
You belied the answer. Motivation for my next question, which is, there is an equivalence of categories. That's usually unsatisfying to me, but you got a result using that. But what can you say what the equivalent actually is, what the functor is? In
Yes,
some
I
reasonable
was
way?
going to play that, but then I thought that I would rather do this story
Well, I
than.
agree, this is great, but I'm wondering,
So
just give us some rough idea what.
So, okay, yes. So here's the story. You're comparing geometric side with some int co. And this int co is acted on by quasi co, always. In tensor, basically, you can tensor coherent sheaves by perfect complexities. So the first thing we do, we make quasi co act on the left hand side. So that's called a spectral action, and it's defined using constructed using Hecke functors, exactly what Dewey's talk. I was hoping to mention it, it didn't get there. And it's a theorem that has a different flavor in each of these three different contexts, but it's a theorem in all three. So that's how you have an action on the left hand side and the right hand side. Now, let's now elide the difference between int-co and quasi-co. Supposing it was really quasi-co. So quasi-co acts on the left hand side, but you want also have a functor. And say you want a functor which is linear. So you only have to specify one object. So I'll say what this one object is. It's the object that co-represents the functor of like first Whittaker coefficient. Like, so there is, you can modular forms do the Q expansion, it's a good, like, it's just simple integral without the Q multiple. And there's analog of that complete, like just a cousin of this construction in geometry. So it's a functor from sheaves on Bungie to vector spaces. Track the first Whittaker coefficient. Co-represented by something, call this object a vacuum Poincare object, and that's the image of the structure sheaf on log cis. So that's the function in one direction. Well, and then you write 900 pages to prove that it's equivalent.
We have a question from Zoom, from the person named from Categorical.
What would that be?
No opinion-based question. How many of these ideas do you think ultimately will have direct analogs in the global arithmetic setting?
Global, I think it's hard to predict. So, so the current program to prove the local partial conjecture uses a lot of that. So one thing they don't have access to is this game with D modules. So like, here we playing geometric constructions against this D moduli constructions, and partial setting so far, we only have access to the geometric constructions.
That's local language.
It's local. Global, there's one person in the world who might have an idea about this. You can guess who that is. I mean, like, I don't know.
So I was just wondering, so when you discussed this Betti geometric Langlands, was the field of coefficients characteristic in the sheets? Was the field of coefficients field E?
I took it so because I'm a coward. But one expects that one expects that to work in general. With some modifications, I'm a chicken.
Is there any relation between the D module results and the?
No. So say one more time.
I mean, so the D module, you explained that the D module result implies the Betti result?
No, I don't know anything like that. So I'm saying the statement makes, so I claim that one can make, I expect that one can make a viable statement with with modular coefficients. I haven't attempted to prove it. More or less optimistic.
Said earlier, theorem has Betti Langlands over Q.
Arithmetic is 0 coefficients. Specifically over C, but then you can pass from one field to another.
What happened when you insert on your equalities Frobenius with some Hecke operators on the left? Or just Hecke operators on the trace Hecke operator on the category of sheet. Yes, is there something on the right?
Yes, it's just give me 1 second. Yes, it's more. You have yes, but in fact you have more. You have it's isomorphism is compatible with excursions. So in fact, what Van Saun constructed is the algebra, the action of the algebra excursion operators here. And in fact, so like if you think carefully, his algebra of excursion operators is actually global sections of O.
So but the answer should be some vector space, right? What is the vector space on the right hand side?
So again, let me say that algebra excursion operators is just it's global functions on the stack, and it acts naturally by endomorphisms of any sheaf, and by its construction, this algebra natural action of global sections of O on this corresponds to the action of excursion algebra here. And Hecke operators, they're just elements in excursion algebra.
I guess to or explicit, if we insert Hecke operator, left-hand side will become cohomology of Stuka. Right-hand side, you insert some logical bundle.
How do you remove Frobenius? Just Hecke operators.
Without Frobenius. Oh yeah, so you mean the categorical equivalence. Oh yeah. So yes, this is the part that I was going to talk about, but I didn't. So there are Hecke functors on the geometric side, and they correspond to particular functors on the Galois side, given as follows. Let me say it in words. So Hecke functor at a given point corresponds to a given representation of G check. So to it, you can attach a canonically defined vector bundle on log sys, kind of the evaluation vector bundle. And the functor on the spectral side is tensoring by it. That's kind of.
You have the trace also.
No. So it's like this is categorical, and then you can take trace of that.
So the vector set is a module over gamma of the structures.
Correct.
Right? So you're saying that some kind of reducible. So there is an open part where it's rank free of rank 1.
Correct. Specifically, irreducible locus.
For question, that thanks, Dennis again.
I'll be around until Tuesday.